Hello and welcome. In this video we're going to look at an application of differentials. So in example 3 we're looking at the radius of a sphere that's measured and found to be 21 centimeters. We can call that r, right, for our radius, with a possible error in measurement of at most 0.05 centimeters. So here the radius could be 21 plus 0.05, which would be 21.05 centimeters. Or it could be as small as 21 minus 0.05, which would be 20.95 centimeters. Just get a sense, just get an idea of things. Ooh, I'm glad that wasn't written right on top of my face there, or behind it. It would be worse. What we're going to do is use differentials, it says, to estimate the maximum possible error in using this value of the radius, the 21 centimeters, to compute the volume of the sphere. Now, one way of doing this without differentials is just to figure out what the volume would be with a radius of 21.05 centimeters and subtract that, that volume minus the volume at 21 centimeters. That would give you some kind of maximum possible error. But here we're just going to use differentials because, like we mentioned, differentials can sometimes be used to simplify calculations. Now I know it's going to seem like, why are we going through all this? But the original volume formula that we're going to write in just a moment has a cubic, and when you take the derivative, it gets a little bit simpler, especially if you were going to plug in a radius into that derivative and then change the amount that you're varying the radius by different amounts. Those calculations would end up being a lot simpler. So we'll just jump in, and we're going to write the formula for the volume of a sphere. So the volume of a sphere is 4/3 pi r cubed. And to use differentials, we're going to then take the derivative of this volume formula, and we get 4 times pi r squared when we take the derivative of 4/3 pi r cubed. And remember, here we're going to have a dv, and here we're going to have a dr. Just as a quick note, we said that dy, the way it's defined as a differential, is it's f prime of x dx. Here y is like v, and then x here is like r, or vice versa. V is like y and r is like x. And then here we have f prime of x, which is like this function, but having taken the derivative of it, take the derivative of that function. Okay, so this dv that we just got, this dv, is approximately the same thing as delta v, which is the real maximum error that we're going to get. This is approximately delta v, the real max error. Again, we're just using approximations. It says use differentials to estimate, so approximate. Now the change in the radius, the little change in the radius from 21 centimeters out to the possible range of values of the radius, is the 0.05. It's the dr. That's the dr right there. Dr again represents a little change in that that radius value. Like dx represents a change in the x values, dr is representing a change in the values of the radius. So what we're going to do is then take this and figure out what the approximated change in the volume is of the sphere, given that the radius is 21 centimeters and that we might have a change of 0.05 centimeters. So this is plugging in r equals 21 centimeters and dr equals 0.05 centimeters. So we get 4 pi times 21 squared times 0.05, which is approximately 277 cubic centimeters. This is the estimated maximum error. That's the estimated maximum error. The true maximum error we would have to find, we're not going to find that right here, but you would take something like the volume at 21.05 centimeters minus the volume at 21 centimeters. That would be like a real error in volume that could happen. But this is just an estimation for that maximum error. Then it says for part B, now find the maximum relative error. Now the issue here is that 277 cubic centimeters, well, that sounds like a lot of possible error in our volume. Oh, and I should mention too that the units here are important to write. You want to write the cubic centimeters because we had radius in centimeters, so the volume will be cubic centimeters, right? You have a centimeter squared from the r squared and then another centimeter unit from the dr, so that's cubic centimeters altogether. But this 277 cubic centimeters, we don't know if that's like a lot of volume change or a little. I mean, you can imagine if the balloon were gigantic, like Earth-sized, then a change in 277 cubic centimeters is not going to be very much change in volume. So what we could do is we could make that volume, that change in volume, relative to the volume itself. So we'll take the dV. Oops. Like this. We'll take the dV and divide it by V. We'll take the change in the volume, the estimated change in the volume, and divide it by the volume. Now here, the estimated change in the volume was given by 4 pi r squared dr. The volume itself, the formula was 4/3 pi r cubed. And here we'll get a couple of pi's canceling. We'll get some r's canceling. A 4 will cancel, and the 3 will flip up on top. So you'll end up with 3 dr over r. And now if we plug in r equals 21 centimeters and dr equals 0.05 centimeters, you end up getting, well, 3 times 0.5 over 21, which is approximately equal to 0.007. So that's the maximum relative error. It makes the change in volume, the maximum error of volume, or the estimated one at least, relative to the volume itself, which this is a pretty small decimal. You can change that into a maximum percentage error by just changing that decimal value into a percentage. Multiply that by 100%. So we'll take the 0.007 times 100%, and that would give you 0.7%. That's the percentage error. So that's not that much change in volume for that little 0.05 centimeter change in radius. Just gives you some perspective. All right, so that's the end of this packet. Thanks for watching, and see you next time.